Hi, my name is George,
I'm Levy.
and
This is
this is our 2023 STEM Challenge. So, we have identified a problem within the school. We've noticed that the I is overly crowded and has led some people to become late to class, and in general makes traffic in the hallways move very, very slow.
we also have another problem, which with freshmen and maybe even upperclassmen not being able to find where their classes are, if it's a new class they've never been to, or if it's just a weird numbering system, such as like the C wing or the D wing. They like weird numbering systems, so it's hard to find where the class is.
And I think it's also important to mention that that's not even just a freshman issue. I mean, me as a senior, I've had classes in the C wing, and I'm like, I can't find where is that. And so we started thinking about all these problems. And initially, we were thinking, okay, well, we can install some sort of roundabout in the eye and try and minimize the flow of traffic. But then we thought, well, that wouldn't really help with finding the classes. And so we think we found a solution that will kind of solve both of these problems. What our solution is a mapping software that can both redirect the flow of traffic and help those who are lost find their class. And the reason why we kind of wanted to do this was because of the problem we stated, but also everybody's already uh, kind of initiated with these mapping programs. And so it won't be a large learning curve. According to Google Maps themselves, 77% of smartphone users regularly use navigation applications. And keep in mind, that is all cell phone users, not even the demographic that's in high school, which is most likely even larger than that. So that will kind of allow us to, if we create an interface that is recognizable and usable, then hopefully people will be able to easily use this on a daily basis.
And also, once they start using it and have been using it for like say a week or maybe 2 weeks, they'll begin to like develop a habit. So they'll know where to go for where to go to their classroom. Even if it's maybe slightly longer, it's going to navigate them away from the eye or away from crowded areas, so they get to their classes overall faster, quicker, and then soon they might not even have to use the app or the mapping system because they already have a habit of where they're going to walk to each class.
Yeah,
And
that's
so
exactly
that's
right.
yeah. So we introduce Garnet Valley Maps to you guys.
So as far as the implementation goes that Levy was talking about, currently we have a demo that we're going to show you in just a second here. And that demo is in the Java programming language. So I'm actually going to go ahead and flip over to that tab real quick. Essentially, the way it works here, and I apologize, my screen shares in the way of the buttons for me to click. Give me just one moment. I can't seem to move that. What we're going to do is I'm just going to minimize the screen for just a second here. Perfect. Okay. I'm going to have to, unfortunately, just extend it over my home screen. What we can do here is we can go ahead and put in a start point and an end point to our map here. And later on down the line, we'll talk about this in just a second. Our start point can actually be our active location, our GPS location that our phone gives us. But for now, for simplicity's sake, we're just going to choose a random point along the map. This is a rough mock-up of our school. And it's worth mentioning that this actually didn't take too long to do because our algorithm does not require any hard-coded values. All it does is it needs to know where each intersection is and the closest intersection to it. So, or the connection intersections. So we're going to start at C104 and we're going to go to F103. If we click start here, we'll see that it's going to find the fastest route for us. And let's say we want to change that up. We want to go from A111 to D103. Oh, excuse me, D103. It's once again is going to find the fastest route. Now, in this scenario, you'll see that it might not have been the absolutely perfectly most efficient route. We could have possibly come down through here and gone around this way. There are very slight inefficiencies in the algorithm we have chose, and I'll show you how our algorithm works. but that can actually be fixed with user data as more and more people use it. As of right now, our working prototype, this is just a prototype, remember, will get users to their class fairly efficiently, almost 100% of the time, and will get them to their class the most efficient route about 90% of the time from our testing. Now, we unfortunately seem to get like a pretty unlucky start here, but just to prove that, I'm going to type in just a few more points, and you'll notice that it actually does do a fairly good job. We'll go to B103 now. And so it really is quite good at finding the best route. So now we're going to flip back to our presentation real quick. And what we plan to do is we plan to take that from a Java setting over to an app, kind of like the Saturn app that a lot of people already use. And this is a screenshot over here of the Saturn app. All it does is it links to Alma. It gets all of the class data, and it goes ahead and shows students how much time's left in their class and what class they have next. Imagine if we could just add a map, an automatic map feature to this, an app like this. This would be a huge tool for incoming freshmen, really anyone at the beginning of a semester. Levi, would you like to talk to us about how we can analyze the traffic patterns with that though?
Yeah, so with this, then we can see where people move, and we can see like, all right, this person took this certain route and they took however long that takes. Say that takes 5 minutes. And then we see, all right, this person took the same from the same class to the next same class, but it took 4 minutes. So what was their route? Where are a lot of people traveling? So if we see, we can follow their data, and we can follow that there's a whole bunch of people in the eye. Then we can find ways to route people around that and go maybe around the other backside and outside to go through the C wing, or however to make it less congested in those areas. This will make traffic move faster in the hallways. There's going to be less people in one area at a time, and it's going to make it easier to put things up in the hallways, such as like on Thursdays, there's Pretzel Thursday. It's easier to put things in the hallway with the cart with pretzels because there's not going to be so many people running into that cart, or it's not going to be in the way as much. And then we can just follow this and keep building onto the prototype and onto the map and make it more and more efficient to find the quickest route and the most efficient route by just following where people go.
And one thing I think is worth mentioning, we already did touch on it, but people start to form habits. So if you direct somebody for the first week or two when they have to still rely on this app to their next class through a certain path, odds are they are going to continue to follow that path. So not only will it prevent people who are currently using the app from going through the eye and causing too much congestion, it will create good habits for people to minimize congestion. So this is where we get into the nitty-gritty of how it actually works. To kind of start, what happens is we choose a start point and an end point, as we just discussed before. So if we choose a start point of C103 right here, what we'll notice is there's actually two different connections that we can go to. We can either go to this classroom right here, C101, or we can go to this intersection point right here. And that's the way our program kind of views everything. It views almost every single line as straight up and down, left and right intersection points. And so it doesn't go from this intersection to this intersection. It actually goes from here to here to there. And the same thing goes here. It goes from this intersection to this classroom, and then to this intersection. And that makes it really, really simple. And so what we can do, for an example like this, if we were trying to go from C103 to F101, what our program is going to do is it's going to measure the distance from C103 to C101, because that's one of the options it can go to, or C103 to this intersection point right here. And it's going to measure the distance from here to there and from here to there. And then it's going to find out how close that each of those points actually gets us to the target value. So we'll see C101 is about equidistant from this intersection right here, but it actually puts us a lot further away from our end goal as this intersection does. So what that's going to do is that process of first finding a distance and then also weighing that distance to figure out, was it worth it to travel that distance? Did it actually get us closer to the target? Is what we mean when we say a weighted distance is established for each point. And then the process from there just repeats. So what the program would then do is it would run down to this intersection and it would say, I could either go left or I can go right. And it's going to run this little intersection right here and it's going to run B101. And it's going to say, well, this one's the best option. And then it's going to go ahead and say, well, I can't go backwards. I was just there. And it will go straight to F101. And that is essentially how it works. But in order to minimize the amount of mistakes that it makes, because this is a slightly flawed method, and we'll talk about how the distance is actually calculated in a second, because that's a very finite detail. But we actually run the path backwards as well. So F101, it will then be trying to find, it will start with F101, and then we'll try and be getting to C103. And then once we do both of those routes, we're just kind of gonna choose the most successful one. And the two distance methods that we were talking about before are x and plus y distance and Euclidean distance. Euclidean distance calculates straight distance values, kind of like the distance formula that we've all learned in math class. Oh, excuse me, that we've all learned in math class. And the x and y distance simply goes ahead and adds the y distance plus the x distance from one point to another. And we found that actually works a little bit better for our purposes, because almost all of these points intersect at 90-degree angles. So it actually makes more sense because you can't really make diagonal lines between most of these points. Levy, is there anything you wanted to add before we wrapped up?
I just want to say, like, this whole system, it doesn't just work on this school. Like, it doesn't only work on this layout. It's since we made the algorithm to work just between connections and distance, this can work on any layout, any school, anything you want to build it in. You can completely change the whole layout of the thing, and that's makes making the map really, really simple, actually.
That's an awesome point. So right now I'm screen sharing all of the connection points that we had to put in. And this might look like a lot, but it is important to remember that each one of these connection points represents a hallway in the school. As far as we have been able to figure out, and we've been put a lot of research into this, this is the most efficient way of inputting the points. All this is this is about a half hour's worth of work translating from a map, simply putting it into the code base. This is not hard coding at all. If we were to hard code every single combination, this is a stat I probably should have run beforehand, but I'm willing to bet it's in the millions of different paths that you could take. So that would not be very efficient. It would create an issue where you have to actually have a large amount of memory in your phone in order to store this app. All you need to store is this text file right here, and you will be able to get to any of your classes. And it will also, in addition to the rest of our code. And if you want to take a look at that, this is just the way we calculate the distance. I don't think we quite have time to go through all of it, but this is all done by hand. None of this was pulled from any GitHub or any of the websites where you can kind of look at what other people have done. We actually did this completely by ourselves with very little help from outside sources. And I think that it is definitely worth taking a look at this if you're knowledgeable of the code. But and if you'd like to do that, all this code will be put into our project file. I believe that is about all that we have. Is there anything else you wanted to say, Levy?
No, I think that's about it.
These are our citations, and we would both like to thank you very much for listening.